Hello and welcome to running the statistical gauntlet in SPSS. We've done R, we've done SAS. SPS is our final gauntlet. I hope you'll join me on this riveting statistical run. I'm Mark Williamson for the Biostats Core at DaCCoTA at the University of North Dakota. So why do a gauntlet at all? Well, let me introduce the concept. So in a lot of introductory statistics courses, a single example or just a few examples are used. This is problematic because it doesn't really help train your eye in understanding examples. It also doesn't help if you just want to adapt an example to your own work and you only have one example to go from. Maybe your work is very different. So I'm trying to remedy those two problems by providing exhaustive back-to-back examples to really get you in the task of understanding what each statistical test is doing. So this is more for intermediate users. I expect you have some understanding and underpinning of statistics and statistical tests, and also a lot of basic things like data exploration, statistical assumptions we skip over to just focus on running bare bones tests. So, with all that out of the way, get ready for a gauntlet. I hope it will serve you well. So before I continue on, some assessment things. We have a pretest you can take here to gauge what you knew beforehand. There should also be links in the description to this video. And after finishing, you can take the post-test to assess how well you did, as well as a short survey that will help us understand how well this helped you. So then, an overview of what is to be done. We'll be using SPSS, and now if you are at UND, you can access it via the sister's workspace. If not, you have to have a copy of SPSS yourself. A really great resource is this link to sample files. It gives a short description of all the sample files SPS has. I'm using almost entirely sample files within SPSS with one exception. So the topics will be covered, three broad categories: t-test, ANOVA, and regression, 3 in each. For each topic, there will be 6 examples. Because this is a gauntlet, I will be ignoring most data exploration, assumptions, etc., and just going right to the test and condensing a lot of the output for brevity. Look at things like the test statistic and p-value. Those will be colored, and then appropriate other variables that are needed to assess the results. I'll outline those by color. And I'll start each of the topic sections with a drop-down menu on SPSS, how to actually access the different tests. And then each example will have a research question, relevant results, the written out answer to said question, and then a figure or table where appropriate. Now, typically you only graph things when it is significant, but I will have some graphs for no results just to show some clarity. All right, let's get ready to run the gauntlet. Put on your armor and go. The data sets. Again, this is from within SPSS's sample data sets, all except for commercial ratings, which can be found at this link here and then should be in the description. So for number 1, we have our one sample t-test. A one sample t-test tests if the variable's mean is different from a set value. So let's show how to do this in SPSS. You go to Analyze, Compare Means, and one sample t-test. Pretty straightforward. And you just put whether value you want, or not value, but variable you want here, and then the test value down here. You can estimate effect sizes, etc. If you need to split your data out, say you only want to look at a specific group, you can go to split file under the data and go from there. So for example, if you want model, you can have groups based by model, so you could look at specific, say, models of car, which we'll do in one of the examples. Okay, let's get right into example 1 of topic 1. For the t-test, we're going to ask, is coffee cake rank lower than average? And average is 7.5. This was a 15-point scale. Look at coffee cake here, mean is 5.19. One sample t-test. The t-value is negative 3.0. 7.9. And since we're saying lower, that's a one-sided p-test, that is indeed significant. So yes, coffee cake preference was significantly lower than 7.5, given a mean of 5.19. I'll start circling some things as well here. Okay, and the same data set of breakfast, is butter toast ranked higher than average? So we'll do the same thing. Its mean is 7.93. It's higher, but is it significant? Well, t-value is pretty low here, and no, in fact, it is not significantly higher than 7.5. Again, using the same data set, is the rank for jelly donuts different than glazed? So glazed donuts ranks is 7.55. Let's see if jelly is any different. Well, jelly is 8.48, so it looks like it's higher, but is it significantly higher? Well, the t-value is 4.65. And yes, that is indeed significant. We're using a two-sided p-value because we're asking different. We're not picking a side. So yes, jelly preference was significantly higher than glazed. Moving along to a different data set of cars, is average car sales higher than 50,000? Well, we look at the mean. It's about 53,000. T-value is pretty low here, one-sided. And so no, it was not significantly higher than 50K. What about specific cars? Is the average Dodge car's miles per gallon lower than average? So the average is 23.84. Dodge's is 20.10. T-value is here. P-value is, yes, significant. MPG was significantly lower. The 20.10 was lower than 23.84. And finally, Ford's different from Chevrolet. So Chevrolet's is 28.4. Ford's ended up being 22.82 with a pretty high t-value. And yes, Ford's was significantly lower than 28.44. So that was our one-sample t-test. Moving on to a two-sample t-test, which now tests if the mean of two different groups is different rather than one group and a constant value. So to do this, we just go to Analyze, Compare Means, and then Independent Samples t-test. And then you have a test variable, so that's going to be numerical, and then a grouping variable, and you need to define groups. And then if you want to build a chart from there, you can go to Graphs and Chart Builder. And in Chart Builder, you want to do a bar graph, and then down here on the x-axis, you'll do your category, and then on the y-axis, you'll do your numerical variable. You can display error bars, clicking this box here, etc. So let's jump into some cars. Is miles per gallon greater in automobiles compared to trucks? When we look at automobiles and trucks, mean NPG of automobiles is 25, trucks are 19. That certainly looks different, but we're going to need to look at our t-value. And we're going to looking at standard deviation. This is about the same, so we can assume equal variances. High t-value, significant p-value. So yes, MPG was significantly higher in automobiles. We see MPG here compared to trucks. What about price between automobiles and trucks? Same sort of thing. We got the two prices here. They look pretty close. And so we see the t-value is very low and p-value is not significant. So no, there was no significant price difference between automobiles and trucks. You notice that trucks were more expensive, but there was so much variability that these error bars overlapped. So we didn't have enough information or data to prove that they were significantly different. Okay, what about going back to our breakfast data set? Is cinnamon bun ranking different between males and females? Their preference. So between males and females, males look like they have a higher cinnamon bun preference, but if we look at a t-value, it's pretty low, and then this is two-sided because we're looking at difference. No, there was not a significant difference between the two. Again, males looks higher, but it was not significantly different. The error bars greatly overlapped. What about hard roll rankings? So like this is like a breakfast roll, hard roll. Okay, well it looks like there's quite a bit of difference here. Well, or more, at least more difference, 8.76 and 10, though the t-value is actually not any better, and no, that is not significant. Hard roll ranking was not lower in males. Okay, looking at 5. This is a different data set on patient length of stay. So if length of stay greater for patients in the control compared to the treatment, well, we got control and treatment. Looks like control had greater stay, but was that significant? T-value, p-value, yes, it was significant. The controls stayed longer than the treatment. What about age for patients in the control compared to the treatment? Well, the mean age looks very close, 72 and 71, and t-value is not significant. So there was no significant difference between age between control and treatment, which is good. That was a good design of the experiment, because you want to have sort of randomly assigned that there shouldn't be any bias between age. So anyways, there we go. That was the two sample. We have now come to our third and final t-test, the paired t-test. It tests if the means of two different paired groups are different. So unlike the two sample t-tests, which were independent samples, these are paired samples. They have some relationship, often a before and after relationship of the same individual, different observations across time. So to do this in SPSS, analyze, compare means, and paired samples t-test. Now you're going to have your variables your measurements in two different variables, say triglyceride levels at one time interval and then triglyceride levels at another time interval for the same patients. Often this sort of setup, you might have something like a patient ID to be able to link the two together, though you don't need to have that in the actual test. Now to plot these, I think a spaghetti plot is usually the best way to show this. And to do that, the easiest way I find in SPSS is to go to analyze and run a generalized linear model and just add a plot to it. So generalized linear model, repeated measures. And in that, you're going to create a factor, and you're going to have two levels because you have just a before and after, two different paired groups. You can give it a name. And then within the repeated measures, you're going to have within subject variables, your factors. So you're going to have like your trig1 and your trig2. And then the between subject factors to show that, how they're linked, you put that patient ID here. And then to get the plot, you want to click plots here. On your horizontal axis, you're going to have your factor. So that's our different triglyceride levels in this example. And then across the separate lines is that patient ID here. You can run that, and then I'll give you the plots. Let's get to our examples. So we've been talking about triglycerides, so let's jump into that. Our triglyceride measurements in patients different between the initial and the first interim visit. So let's look here. Looks like there might be a difference, 38 and 24. But when we run that, one important thing that our analysis will pull out is correlation. It tells how correlated the two are to each other, and that can often be significant. And so there's fairly low correlation between the two. But then looking at our paired samples t-test, we see a t is fairly low, 1.7, and the two-sided p, because we're asking if there's a difference rather than a one-sided, is not significant. So triglyceride measurements were not different, and this is our spaghetti plot. We can see that between time period 1 and 2, some levels went up, most went down, but not strongly enough to really be different. What about between the initial and the final visit for triglyceride? Is there a difference? So we look here, looking pretty close to the same, a little bit different correlation, and we see a t-value even lower, so no, again, it's not significant. You can see that here that there seemed to be less of a pattern. So there we go there. Now looking at the same patient data set, but now let's look at weight measurements. Are they lower in patients between the initial and final visit? So let's see if weight's any different. We had 198 and then finally 190, so loss on average about 8 pounds. Pretty high correlation, so there's really strong correlation between patient's initial and final weight. So, and high t-value, and this was significant. Yes, so weight was significantly lower in the final visit, so patients lost weight between these measurements. Turning back to our snack food. Is glazed donut preference difference between overall? So this is no longer in time like a lot of ones. These are between groups, between overall and snack preference. So you could say, do you like glazed donuts just overall, or do you like glazed donuts for snacks? So the same individuals ask different questions about their preference for glazed donut. So overall in snacks, looks like snacks is lower at 5.3, but is this fairly highly correlated? High correlation usually tends to lead to significance, but a little bit different question being asked there. So you can't just rely on that. Anyways, t-value is 4.2. P-value is significant. Yes, glazed donut preference was higher overall compared to just a snack. Okay. Moving on here, we'll keep with the food. Our blueberry preference is higher in breakfast compared to snacks. So breakfast and snacks, it looks like there's very little difference. And again, very low correlation, low t-value, not significant p-value. There was no difference in preference between breakfast and snacks for blueberry muffins. They're liked about the same for those times of eating. What about English muffins? In a special kind of breakfast, a cereal-only breakfast, let's switch to a red pen here, in cereal-only breakfast compared to a bacon and eggs breakfast. So if you have just cereal and an English muffin, do you like English muffin more compared to English muffins with bacon and eggs? Again, seems like there's about a 1 point difference, 5.62 and 7.2, fairly high correlation, fairly high t-value, and yes, a significant p-value. So English muffin preference was significantly higher in cereal breakfasts. That was factor 2 here. So I'll just write a little C for cereal. They like them more than cereal in cereal breakfasts. Now we are on to ANOVA, which can be considered the extension of a t-test with more than 2 groups. So a one-way ANOVA test, if a mean is different between the category with 3 or more groups, it's the simplest ANOVA. So to do this in SPSS, analyze, compare means, and one-way ANOVA. Simple as that. So then you're going to need a dependent variable. That is going to be your numerical y variable, and then your factor variable, so that grouping variable. And helpfully, you will probably want to do a post hoc test to tell what specific groups are different. This will pop up here. You can use wherever you want. I'll be using Tukey. Feel free to use what post hoc test you find most appropriate. Then you can also go to the options section, and I like to click the descriptive statistics, which gives me the means of my group, so I can kind of gauge how different they are prior to the test. Now, sometimes you're going to need to select specific parts of your data. Say you have groups with more groups than you want. Say you have like 10 car brands, but you only want to look at 3. You can select your data to just have those brands. So go to data and then select cases. Now this will pop up here, and you can figure out how you want it set up. I really like this any function. So you do any and then whatever your variable is. So for the group here is yield for this example. And then I want yield groups 2, 3, 5, and 6. You can see I didn't need to have in a certain range or anything. You can select all of it. I could say 2, 5, 6, or 3 and 7, or whatever you want. So this select casing with the any is really helpful. Now to graph this would be very similar to the 2-sample t-test. You'll use a bar graph. You use your grouping variable down here, your y variable up here, and of course use the error bars button here. Right then, let's get down to business. Looking at sales data, our sales training course performance scores different across group. So this is our initial ANOVA. We're going to look at our test statistics as the F value, and this is indeed significant. So now we can go and look at our multiple comparisons. So this is where it gets a little tricky here, but I'm going to pop up just the descriptive statistics to help us along here. So we had 3 different groups, and These are our mean performance scores, and we can see that group 3 had the highest, while group 1 had the lowest. And so what these multiple comparisons with the Tukey's test is doing is comparing each group to another. Some of these numbers are redundant, so let's work together here. These are the important comparisons: 1 to 2, 1 to 3, and then 2 to 3. That gives all the comparisons. So it looks like 1 is significantly different from 2, and 1 is significantly different from 3, but 2 and 3 are not significantly different. And this can be shown in the graph here and summarized in our results. So this had the highest, it was significantly different from 1, and 1 was significantly different from 2, but 2 was lower than 3, but not significantly. Okay, turning to a crop example, our aflatoxin level is different across yields 1 through 4. So I selected just yields 1 through 4. The F value is significant, so let's do some post hoc multiple comparisons. So this is a little more complicated. Of course, every time you add another group, the comparisons get more unwieldy, so just beware. So again, I like to do descriptive statistics. Looks like group 2 has the highest mean, while group 4 has by far the lowest. So these are the comparisons that are useful, and I'm not going to go too much into them nitty-gritty, but essentially yields 2 and 3 were significantly higher than 1 and 4, but not from each other. So 2 and 3, you can see the error bars overlap quite a bit. So these were the highest, etc. Now let's look at aflatoxin levels across yields 2, 3, 5, and 6. We find with ANOVA a very small F value, not significant, so I'm not going to show the post hoc comparisons. Instead, I'll just show you the descriptive statistics, and you can see they're all very close to another. And so no, there was no difference in yields across these specific groups. Pulling back here, let's just look at every yield, yield 1 through 8. And this is significant, unsurprisingly, because we saw some difference is in subsets of yields. And we can see here with the descriptive statistics, again, I'm not going to show the comparison table because it's so big. Comparing all these groups, it would just take up the whole slide. But we can see that it ranges from the smallest of 8 something to like the 33s. So let's show a plot here, and I'm not going to go through all the exact comparisons of what's significant, but we can see here that yields 2, 3, 5, and 6 are kind of this high measurement, whereas 1 and 7 are kind of in this more middle one, and then the lowest is definitely 8, and then 4 is kind of intermediate between these two. Okay, trucking along here, we'll switch data sets and look at carpet cleaner preference in consumers across package type. So we find that for ANOVA, high F value is significant, so we'll do a post hoc. So the different package designs are A, B, and C. And here are the mean values. You can see that A is quite a bit higher than the other two. And so what we see here is that, yeah, A is significantly different from B and C, but B is not significantly different from C, and we can show that here. Unsurprisingly, package A had significantly higher preference than B or C. What about cleaner preference across brand? Again, we can do this, but looks like that is not significant at all. Across the 3 brands, K2R, Glory, and Bissell. While Glory was the highest, there's so much variation that there wasn't a significant difference across brand. Okay, we've mastered one-way ANOVA, or at least gotten our feet wet in it. Let's turn to two-way ANOVA, which tests if a variable's mean is different between 2 categories with multiple groups each. We can do this with a general linear model under Analyze and Univariate. And then what we can just do here is our dependent variable as preference, and then our fixed factors. So you could have brand name and good housekeeping seal. These are categories. And then if you want to look at, say, the interaction between these 2 categories, you can go to model here, which will pull this up, and then you can build interaction terms. So you can have brand seal and the interaction between brand and seal. You can also do those post hoc tests for your different variables. Again, I'm using 2 keys. I also like in the options to do descriptive statistics. And again, if you need to select cases, you can use the select cases drop-down menu. And in this case, I'm using these conditions where it's say like a manufacturer, and then since these are, instead of numbers, categories, I'm doing things like Dodge, Ford, and Toyota, where I put them in parentheses rather than those raw numbers, depending on what data you had. Those yield data were numerical, even though they are categories. These ones are clearly names as categories. Getting into our examples, let's look at our carpet cleaner preferences again, but against 2 categories, brand and seal. So just some descriptive statistics here. We can split it out by both brand and seal, and we can see the differences. Not as useful to try to parse out here, but here we go. So let's go to our test of between subject effects. So this is our ANOVA. And the important ones here are brand, seal, and then the interaction. We can see that it turns out that there's no significant variables here. And unsurprisingly, there's a lot of variation. All these error bars overlap, so there's no difference between brand, seal, or the interaction. What if we're looking at brand and package? Well, then again, we have descriptive statistics. We have 3 different brands, 3 different packages. Looks like there might be more of a difference here. But let's take a look here. Looks like while the brand and interaction are not significant, the package is indeed still significant. And so let's look at multiple comparisons for that package. And what we see here is that, again, just like we saw with one-way ANOVA, A is a lot higher preferences than B or C. And so only only packages was significant in this more complex model, comparable to just doing a one-way with package alone. Looking at car manufacturers, let's see if there's MPG difference across types. That's automobile or truck, and then 3 types of manufacturers, Dodge, Ford, and Toyota. Descriptive statistics show that, yeah, there's some variation, but let's really look at the test here. Looks like type and manufacturer are simply different, but the interaction is not. Looking at multiple comparisons, looks like Dodge is significantly different from Toyota, but the other Ford is not. So what we can see here is, yeah, Toyota is the highest, Dodge is the lowest, and these 2 are significantly different, but Ford is in the middle. And again, we don't really need to do this because it's just 2-way. We can see clearly that since they're significantly different, the higher one is automobile MPG. And we've already saw that through a t-test. So yeah, MPG was significantly higher in automobiles, and MPG was significantly higher in Toyota compared to Dodge. Now, if we look at car price numbers across type again, but then 3 different manufacturers, Chrysler, Mitsubishi, and Nissan, find that it seems to be a lot closer with the car price. I think this is price in thousands. And we find that actually all 3 of them are not significant. And one reason why, too, is looks like, in fact, Chrysler doesn't even have any trucks in that category, so this was a poorly set up design on my end anyways. But, you know, trucks had such high variation, wasn't any difference, and then just across brands didn't look like any difference at all. Okay, let's keep going here. Let's turn to a nurse data set. Our hourly nurse wages differ across position and age range. So the different positions are hospital or office, those are the 2, and then age range is either 1830, 31 to 45, and 46 to 65. We look at this with our 2-way ANOVA. looks like that both position and age range are significant, but the interaction is not. So looking at multiple comparisons for both nurse type and age range, we find that wages were significantly higher in hospitals compared to offices, and wages were highest in the top age range. So the older you are, the higher you're getting paid, probably because it probably has to do with things like work experience. But let's actually look at that specifically. We're going to ask wages different across age range and then specifically experience, not just age, which may be a proxy for experience. So again, we have the same three age ranges, but then the years of experience go from 5 or less, 6 to 10, 11 to 15. And what we find here is that with the experiences year scale, looks like with that in the model, only that is significant. So age range was sort of a proxy for it, which is unsurprisingly so. The years of experience, and I guess you can see here, there's actually more years of experience the higher up you go, because this is also a little bit poorly selected on my part in some ways, because these lower age ranges don't have these higher years of experience. But anyways, that being said, what we see here is that at age range increases, there were higher salary, and I think like ones right next to each other usually weren't significantly different, but then if there's at least one iteration, like these are significantly different and these are significantly different, etc. If they're immediately adjacent, they're too close to each other, but if they're spread out, they start to become significant. So unsurprisingly, as you get more experience, you get more pay. Now then, let us turn to what I am calling advanced ANOVA, testing if a variable's mean is different across categories, so just like a normal one-way ANOVA, but while accounting for things like blocking, nesting, or repeated measures. So this can be done in a couple different ways here. First of all, for the repeated measures, you can go to power analysis, general linear model, and then repeated measures. We've seen this before when we were doing some spaghetti plots. You're going to need to have your factors, and then name it whatever you want. And then, so each of these factors are the repeated measures. And then whatever, if you have like IDs, you can put it down here. You can add that to make things like spaghetti plots. Now, if you want to do things with like nesting repeated measures, you'll use general linear models, but use the univariate. And then you can set up your model. And to do things like nesting, you will need to build custom terms. So for example, if we had two variables, neighborhood and town, and we know that neighborhoods are nested in town, we need to build terms that have neighborhood within town. So it's like town, and then within it, neighborhood. That's the setup here. Additionally, you might need to select cases. For some of my examples, only use a certain amount of like towns or neighborhoods. And we've already seen the any function, but you can actually do this for multiple variables. So you can do that, like select specific neighborhoods and also select specific towns or whatever your categories are. Okay, with that, let us jump into blocking. So really blocking is going to be, you have a category variable you're interested in, but you add other variables to sort of as random effects to control for variability. So we're going to say, is revenue different across product while controlling for continent? So here are our products here. We did this ANOVA, and what we see here is product is not significant. So even after controlling for continent, which had quite a bit of variability here, there was no difference between product type. Additionally, we could look at another blocking example. Is shampoo pH different across shift while controlling for batch? Again, We're looking at the working shift, night, morning, and afternoon, but then we want to control for batch as well as things like the interaction between them. We see that shift is significant, including our batch variability. So we can do multiple comparisons, just like a normal ANOVA, night compared to morning, and afternoon and morning compared to, I guess, then afternoon. Those are the three comparisons we want. And what we find is they're all significantly different. So afternoon shifts were significantly higher than morning shifts, which were significantly higher than night shifts. Though there wasn't quite a lot of variability. So even though this is significantly different, the overall actual difference isn't too strong. Okay, let's go to our nesting ANOVA, advanced ANOVA. So we're going to say, look at this voting information is gas tax opinion, so how you feel about it. Different across neighborhoods. We're going to look at neighborhoods 2 and 5. We'll nest it in townships 2 and 5. So here are, and this is usually a cross tabulation. So this is frequency data. I found the best way when we're looking at this sort of data to make sure we have enough in all categories. You see neighborhoods 2 through 5, and then townships 2 through 5, and yeah, there's between like 61 and 260, 270 people per neighborhood in a township, so that should work. So we run these factors with our neighborhood, our town, and then the nesting factor, and right now we could look at like things like neighborhood and town as both important, but I'm just interested in neighborhood while nesting, and what we find is that there's no difference while nested in township. Then I could ask about gas tax opinion across neighborhood when nested in county. So we have more counties: eastern, central, western, northern, and southern, and then I did all these neighborhoods. Run this, and what we found here is now neighborhood is significant. So there was a significant difference when nested in county. Neighborhood 5 had the highest means, while 3 had the lowest. And those at least were significantly different from each other. Now let's move on to repeated measures ANOVA. We'll ask with some commercial data, are there differences between commercials across 4 successive commercials? We have appeal for first all the way to the 4th. It looks like it goes up. So then we'll run repeated measures. One of the things it gives is a test of sphericity. That's one of the assumptions of repeated measures ANOVA. And it is this value here, that significance value, so it has its own p-value. That's not significant, so we can assume that the assumption of sphericity is upheld. So there's different sort of outcomes here at different f and p values. So we can use the sphericity assumed value. Decide that, well, it didn't really matter what we did, but in any case, that was significant. So yes, commercials 3 and 4. So we see these at the highest ones had significantly higher ratings than 1 and 2. Again, we can look at our shampoo example data set again, but in this case, look at more along the lines of repeated measures. Differences in shampoo pH across batches, considering batches. So we have 6 different batches. We run this again. Sphericity was not significant, so we can assume sphericity. See, this is a very small f value, or actually not small. That's an 8. It's kind of hard to tell. So yes, there was significant difference across batch. The main thing here I think would just say is batch 3 had the highest. I'm not going to parse out all the specific differences. Right, we have left the realm of ANOVA and entered into regression. So let's start simply with simple linear regression, which tests if there's a relation between a numerical responsible and a single numerical predictor variable. So these are all numerical now. So to run this in SPSS, just go down to regression under analysis and then run linear. And then in here, you can have your dependent variable, so your y variable, and then your numerical x variable down here. If you want to plot this, you You can go to plots, chart builder, and you want to go your scatter dot plot. So your X variable is going to be down here. Your Y variable is going to be here. And with that, and you can add like a linear line as well, a linear trend line. Okay, with that, let's breeze through some examples. Looking at sales, can sales be predicted by advertising spending? So we're running a regression. It calls it ANOVA because ANOVA and regression are sort of two sides of the same coin in many ways. So just breeze over that. But the main points we're looking for here is going to be our F value and significance value for the overall model, regression model. We see that this is significant, so there's a significant relationship. To kind of tease out what that is, the coefficients down here, there's the beta value, and then our t value and significance. There's the constant, also known as in other models or in other software as like intercept. But we're really looking for our advertising spending. That's a variable of interest. So this is again significant. And when we plot this, we see that yeah, there was a significant positive relationship as advertising spending went up, sales increased. So let's keep moving along. Let's look at men's clothing sales specifically by print and print advertising. So let's get a little more specific. We find that the overall model was significant, and specifically our X variable was significant, and there was a significant positive relationship again between advertising and clothing, though not as strong. We can see here one of the nice things, it plots like the R squared, kind of how much variation is explained by the X variable. This is like in the 8s. This is much lower. Okay, we'll keep going along. Let's look at women's clothing now and customer service. Find that was again significant on all accounts, and it was strongly significant as the number of sales representatives increased. Women's clothing sales increased as well. Turning to a non-clothes example, let's look at car price predicted by MPG. So our more expensive cars, they have different MPG. We see that was significant. Now we have a negative t-value. That means there's going to be a negative relationship. So there is a significant negative relationship as fuel efficiency increased, price decrease. So all the really, what that kind of means is cars that don't get very good gas mileage, so maybe big trucks or vans or sporty cars tend to be more expensive. And if you have high MPG, you probably have a smaller, more compact, more friendly on the bank books type of car. Okay, keeping moving on with car sales by fuel capacity, and this time the model is not significant, and so I'm going to plot it anyways, but there's no significant relationship between fuel capacity and car sales. People don't buy cars based on fuel capacity. There's not really a clear link at all. But then let's look at car resale value. Can that be predicted by price? And that is a huge F value, very significant. And yes, indeed, there is a very strong relationship. The more expensive your car was to begin with, the more expensive the resale price will be. So there we go. Let us extend into multiple linear regression. This is test if there's a relation between a numerical response variable and now multiple numerical predictor variables. So to do this in SPSS, pretty easy. Go to linear again. And just like in linear regression, you have your Y variable up here, but instead of just one X, you can have 2 or more X variables down here. Not much more to it. Okay, let's take a look at our first car example. Can car sales be predicted by width and fuel capacity? So we run this, and now this becomes more important to look at both the overall model F value and P value, and then the specific T values of the variables. Because like in simple linear regression, if the overall model is significant, well, the single variable would be significant. But in this case, if there is a significance in the overall model, you have to parse out what specific variables using the t-value and their associated p-value to get which ones are significant. Now in this case, the overall model is not significant, so therefore neither of the variables significantly predicted car sales, not width nor fuel capacity. Let's look at car MPG instead and look at horsepower, width, length, and curb weight. We find that the overall model is significant, so now we can turn to the t-values of the specific variables. And what we find here is that horsepower, length, and curb weight were significantly predictors of car MPG, but width was not. This is not significant. And to tell sort of the strength and direction, let's look at the beta values. So as horsepower and weight increased, you see that these are negative betas, which means that as those go up, MPG goes down. Conversely, when length increased, MPG increased because this was positive. So that's how you read that. You don't normally plot multiple linear regression because there's too many variables. So you look at the beta values. It looks like SPSS has both unstandardized and standardized coefficient beta values. I guess you can use either one depending on what you want. Okay, let's move on to insurance claims. Can they be predicted by coverage and deductible? Well, the overall model is significant, so let's turn to our t-values of the specific variables. It looks like those are not both significant. The amount of coverage was highly significant, but deductible was not. So and it says this is positive, so as amount of coverage in thousands increased, so did claim costs. Another example with insurance claims we're going to add in income as well. We have, again, significance, and it looks like income was significant along with coverage, but again, deductible was not significant. And these were both positive, so as coverage and income increased, so did claim costs. Turning back to our clothing information, let's look at men's clothing, see if we can predict them by multiple variables: catalog, phone line, print advertising, and rep number. So a number of these things, their overall model is indeed significant. When looking at these, we find that number of catalogs, phones, and print advertising was significant, but customer service representative number was apparently not important to men's clothing sales. And all of these significantly were positive predictors of men's clothing selling. Now looking at women's for the same sort of thing, this is again significant, though it's interesting to note that while customer service representatives, catalogs, and amounts spent on print were significant, phone lines, the number of phone lines open were not. Again, these were all positive associations between sales and those numbers. Okay, last on our list here is logistic regression. So this, like other regression tests, if there's a relation between a response variable and other predictor variables, but in this case, our response variable is not numerical in the classical sense, but is binary. So there's two options: 1 or 0, yes, no, dead, alive, etc. And you can do one or more predictor variables, so you can do essentially almost like simple or multiple linear logistic regression. But anyways, I digress. To get to this, we go to under analyze regression. We're going to do binary logistic. You can do things like multinomial logistic, but that's beyond our gauntlet here. Those are other wars to fight. Now, one thing you might be needing to do here more often with logistic regression is cross tabulation. We've shown that a little bit with some of our other examples, but here's how to do it specifically. Go to descriptive statistics and crosstabs, and once you go in there, you can essentially add your rows and columns, and then in the cells display you can do things like the observed, and like percentages in the rows, etc. So you can see how many individuals are in each of your groups. Let's get started here in our examples with insurance claimant. So can marital status, yes or no, be predicted by claim cost? We'll run our logistical regression. Now instead of an F or a T statistic, we have a walled statistic here. So we'll look at that for significance, and this was not significant. So I'm going to plot it like this. Scatter plot. It's not the best plot, but if you want, but I have a hard time getting them succinctly in SPSS. So if you want good logistical regression output plots, I suggest doing RR-SAS. But in any case, this was not significant, so there's no significant relation between claims cost and marital status. So this is our X variable, cost of claims in thousands. You can see there's really no difference between married and unmarried in sort of the distribution. What about retirement status? Yes or no for insurance claimants? And looking at two variables, claim cost and coverage. Well, we can run that just as easily. We have two walled statistics. They are both significant. And so I'm going to plot these. And so retirement status, so the yeses are up here, was significantly predicted by cost, claim, and coverage. So this is claims, this is coverage. As claim cost and coverage increased, the probability of being retired decreased. So if you're making high cost claims or you have a lot of coverage, you're much more likely to be not retired, so still actively working. Okay, let's move on. Now those two were numerical. We'll continue with our numerical X variable values with can HIV status be predicted by assay. So we're going to treat these assays like 1 to I think 9 as numerical. And what we see here is there is a significant value, and so this is where we're going to get the crosstab to kind of be able to figure things out rather than try to plot things. And we see, yeah, HIV status was significantly predicted by assay, when assay was treated as our numerical variable, as we did here. As assay number increased, so as we go up here, the probability of being HIV positive increased. So you see here at assay result 1, there's only 3 who are HIV positive and most are negative. But as you go up all the way to like some 8, like almost all of them are positive. So this assay is capturing that. Whereas another way of putting it, the probability of being HIV negative decreases as assay goes up, because you start out with almost all being negative, but then as it increases, the probability of being negative decreases. So either way you want to put that. But we can also consider these assay results as categories, because you can do logistical regression with categories, and that's pretty common. We're going into the sort of linear model sort of realm, but that's fine here. Let's run this again, but have them set as a category, set as a category variable. And what we see here, looking at wall variables across all these categories, these are all significant. And then this XB, this is another way of putting this. This is the log odds. Sorry, that's pretty messy. Log odds. And so the reference variable is assay result 1. And so again, this was HIV status was significantly predicted by assay, where assay was treated as a category variable compared to the reference category 1. The odds of being HIV positive were higher in all other categories, increased for each successive category. So this log odds sort of means, what that means is the odds compared to the reference. So it's at higher than 1 odds, and it just keeps going up here. Okay, let's see if we can get some clear categorical variable linear regression going on. So can past voting outcomes be predicted by sex? So again, I do some cross tabulations to sort of feel it out here. So there's male and female, and then whether they voted or not in the last election. You can see percent with gender. So it looks like if you were male, about 60% of males voted, or about 61% of females voted. So is there a significant difference? And when we run the walled statistics on gender, we find that that was not significant. Yeah, they're essentially the proportions were the same. And another way you could see that of this log odds is between male and female is the odds were really no different from one. Or sorry, these are the log odds. These are the intervals. So there's no real difference. What about past voting outcome by more variables? Well, we can cross tab out more. We can look at age category because we've already seen sex over here, so I'm not going to do the cross tab again. And we can also do our county. And we can see there might be some differences here. Ranges between like no's of like 65% all the way down to something like 58%. So that might be significant. Ages looks like low of 53 and high of like 68. So there seems to be more variation. But we're going to run this. And what we find here is, yeah, that for like age categories and counties, looks like there is significance. So I'm going to just read out this because it's sort of hard to parse out quickly, but voting outcome was indeed significantly predicted by age category and county, but not by sex. You can see here that this wall variable is not significant. Members in older categories, so as age goes up, were significantly more likely to have voted in the last election. You can see that the log odds increase, which means it's more likely the older category than the reference young category. And then members in the central and western counties were significantly less likely to have voted than the eastern county. Northern and southern are not different. And we can pick that out by referencing eastern. You have to, because these don't have the specific county names, you have to sort of connect the dots here. Anyways, there we go. All right, we've gotten through our SPSS Gauntlet. SPSS is definitely my weakest statistical software platform. I prefer RSS, but hopefully if SPSS is useful for you, this was helpful for you as well. So here's just some references on the images and selected references that I used. And then as always, I'm part of DaCCoTA, so if you found this helpful, please reference us accordingly. Thank you and have a great day.